Hi everyone, I'm Hyun-Myung, a PhD student from Texas A&M University. Professor Myung is my advisor. Today, I'd like to make a presentation about RNA structural alignment. Here's the outline. I will start by introducing RNA structural alignment. Then, I will explain the proposed structural alignment algorithm with the experimental results. And I will finish with some concluding remarks. RNA is a single chain of bases which are A, U, C, and G. RNA is a very important molecule in biological systems because it is involved in coding, decoding, regulation, and expression of genes. Let me talk about the nature of RNAs. RNA is transcribed from DNA, and RNAs called mRNAs are translated into proteins. There are special RNAs called non-coding RNAs that do not code for proteins, and interestingly, they typically fold onto itself and form a secondary structure. Basically, A is paired with U and C is paired with G. Non-coding RNA plays critical roles in biological systems, and the secondary structures often determine the functional roles. We have a toy example of an RNA family that has three RNAs where they have different sequential compositions but have the same secondary structures. Such variations potentially made by compensatory mutations that change sequential compositions while maintaining their secondary structures. Studying RNA is very important, and RNA alignment is one of the most efficient ways to study RNAs. RNA sequence alignment arranges input RNAs such that the homologous regions are aligned. RNA alignment can be used for transferring annotations of the well-studied RNA to less studied RNA, finding a novel RNA that belongs to the same RNA family, and finding out the evolutionary relationships between RNAs. Here, we have a very practical question: how to align RNAs that have very different sequential bases. RNA structural alignment will probably be the first answer we are looking for. RNA structural alignment arranges RNAs by investigating their similarity in the base and structural levels. This is one of the classical approaches. For given two RNAs, it jointly estimates the consensus secondary structures and RNA alignment. This approach is known to be very accurate at the cost of very high computational complexity. Due to excessive computational complexity, we had two questions. First, is the joint estimation necessary for the accurate structural alignment? And second, can we quantify the degree of structural similarity between bases that belong to different RNAs without the explicit consensus secondary structure estimation? The answer was yes. Topaz was one of the pioneering works which took a network-based approach. Topaz converts RNAs into networks where nodes represent bases and edge weights between the nodes are base pairing probabilities. In this manner, the network naturally contains information about the potential secondary structures of the RNA. Then Topaz utilizes a network aligner to quantify the degree of structural similarity between nodes that belong to the different networks. At this moment, one may have a question. Why do we use the network alignment? Network alignment algorithms are designed to efficiently find the optimal mapping between networks such that the matched nodes that belong to different networks have high node level similarity and structural similarity. Of course, we cannot fully utilize it because network aligners do not consider the order of bases. Topaz only took the first step that computes the node correspondence score. This is the workflow of Topaz. For the input RNA pair, it converts them into networks and computes the node correspondence score based on the isorank and message passing algorithms. Then the alignment is constructed based on the optimal global sequence alignment algorithm. Please note that we do not have the consensus secondary structure as output. However, in practice, we are more than often interested in the alignment itself. We noticed that although Topaz is very effective, there might be things that can be further improved. First, isorank combined with message passing involves iterative computation to obtain equilibrium probabilities as node correspondence score, which is computationally unfavorable. Second, in some cases, a random walk model on which isorank is based is not sensitive enough to accurately measure the local structural similarity score between nodes. As a result, we went back to the original question. Can we more efficiently and better quantify the structural similarity between nodes at both global and local scales? Again, the answer is yes. Recently, we developed a state-of-the-art network aligner called Monaco. Monaco is the most accurate algorithm we have ever tested on diverse benchmarks. Monaco accurately quantifies the structural similarity between nodes through an optimal matching of neighborhoods for alignment of common network regions. Furthermore, Monaco iteratively updates the local structural similarity score to propagate the score over the whole network. Monaco is a very fast algorithm. The structural similarity scores are computed only for selected node pairs, which greatly reduces computational complexity. Besides, due to its high accuracy of local structural similarity score, the performance sharply increases within the small number of iterations. This is the workflow of the proposed algorithm. As you might notice, we designed our algorithm by simply replacing the first step of the Topaz with the structural similarity scoring framework from Monaco. Due to time constraints, I won't explain all the details of the algorithm. However, I would like to explain the key idea for how Monaco quantifies the structural similarity score between nodes. Before starting, there are three types of similarity scores between nodes in different networks that I would like to clarify. The node similarity score is a real value quantifying the relatedness of two nodes at the primary sequence level, which will be given. We can easily compute this score through existing software such as pair HMM or message passing. The structural similarity score is a real value indicating the degree of similarity of two nodes by comparing their surroundings, which is what we want to accurately quantify. Node correspondence score is a real value that summarizes the overall similarity between nodes. Typically, the node correspondence score is a linear combination between node similarity score and structural similarity score. Like what I said, Monaco is an iterative approach. We initialize the structural similarity scores with the values of the node similarity scores. Suppose that we have two networks converted from two input RNAs, and we compute the structural similarity score for the node pair 4 and 3. In this case, we called the node pair 4 and 3 a focal node pair. A black line is a weighted edge whose weight is equal to the base pairing probability. This can be easily computed via existing software, such as RNA-fold, RNA-alifold, or PART. We first construct two neighborhood sets of nodes that are directly connected to the focal nodes. As you can see, 1, 3, and 5 are neighbors of the focal node 4 in the first network, and 1 and 4 are the neighbors of the focal node 3 in the second network. This figure shows the simple rearrangement of the neighborhood sets. The yellow line is the structural similarity score in the previous iteration. Like what I said, it will be the node similarity score at the beginning. As a second step, we find the optimal one-to-one matching between the neighborhood sets based on the structural similarity scores and base pairing probabilities. Specifically, we convert each structural similarity score into the weighted structural similarity score by multiplying the structural similarity score by the base pairing probabilities. The purple dashed line is the optimal one-to-one matching. Note that the optimal matching is equivalent to the optimal local consensus secondary structure. The updated structural similarity score is a weighted sum of the structural similarity scores in the optimal mapping. In this case, the updated structural similarity score for the node pair 4 and 3 is 0.765. Why Monaco is accurate? Monaco framework directly compares the local neighborhoods to quantify the local structural similarity of the focal nodes. Conceptually, Monaco evaluates how well we can match the given focal nodes by comparing their neighborhoods, or in other words, to what extent the local neighborhoods support the alignment between the focal nodes in a potential network alignment. Monaco is also very efficient. The structural similarity score is computed only for node pairs whose node similarity score is positive. And due to its high accuracy of the local structural similarity score, the performance sharply increases within the small number of iterations. In this case, we used only 5 iterations. Let me skip these slides. For those who are interested in Monaco, please refer to the manuscript. For the performance comparison, we selected 2 algorithms. The first algorithm is the best and unique network-based approach Topaz, and the second is TurboFold 2, which is one of the best algorithms based on joint optimization. We used BR-Ally-based 2.1 K2 dataset, which is the golden benchmark dataset for comparison of the structural alignment algorithms. After pre-processing, we had about 8,500 RNA pairs. This is the comparison of the algorithms in terms of sensitivity. The higher, the better. To compute the sensitivity, we compared alignment results from aligners with the ground truth alignment. The true positive value is the number of base pairs that are correctly aligned. False negative is the number of base pairs we miss. As you can see from the box plot, the sensitivity of the proposed algorithm shown in the red box was very competitive. PPV is the ratio of the true positive to the sum of the true positive and false positive. False positive is the number of base pairs misaligned. Similarly, the PPV of the proposed algorithm shown in the red box was very competitive compared to those of the other algorithms. This is the time complexity comparison on a log scale. As you can see, the proposed alignment algorithm was the fastest among the algorithms. I'd like to emphasize that TurboFold 2 has been implemented based on C++, while Topaz and the proposed algorithm have been implemented via MATLAB, which is known to be much slower than the C++ in practice. Even with the fact the proposed algorithm noticeably faster than TurboFold 2. These are concluding remarks. Traditional RNA structural alignment algorithms have suffered from high computational cost due to the joint estimation. The proposed alignment algorithm inherits all the advantages of the network-based approach from Topaz. First, the proposed algorithm is not constrained by the types of secondary structures. Second, the computational complexity of the proposed alignment remains very efficient as the proposed alignment algorithm does not jointly estimate the consensus secondary structure and RNA alignment. The proposed algorithm is as accurate as the state-of-the-art algorithms are. It is because of that the proposed alignment algorithm accurately computes the topological similarity score through an optimal matching of the neighborhoods for alignment of common network regions. The proposed alignment algorithm is the fastest. The time complexity of the proposed algorithm is significantly faster than those of Topaz and TurboFold 2 on average. There are 2 reasons. First, structural similarity scores are updated only for node pairs whose node similarity score is greater than 0. Second, thanks to its high accuracy of the structural similarity score estimation, the proposed structural alignment algorithm achieved very high accuracy with only 5 iterations. We have some references here. Thank you for watching my presentation. Please leave any questions if you may have. Lastly, I would like to express my special gratitude to the special session organizer, Professor Gail Rosen, for giving us such a great opportunity to present our research.